A 2.4 meter diameter merry-go-round with a mass of 240 kilograms is spinning at 20 rotations per minute. Maybe revolutions per minute. Not sure. That's okay. We're fine with this. Jean runs around the merry-go-round at 5 meters per second in the same direction that it is turning. Jumps on to the outer edge. John's mass is 33 kilograms. Okay. So I'm going to start by drawing a picture. Merry-go-round. John. Merry-go-round is spinning this way. John is running this way. He is going at 5 meters per second. And the diameter of the radius, actually I'm going to draw it this way. The radius is going to be 1.2 meters because they give us specifically a diameter. And the omega, I'll call it M for merry-go-round. I guess John and Mary, that makes sense. 20 RPMs. Yep, and then John's mass equals 33 kilograms. And mass of Mary is 240 kilograms. So the idea here is going to be conservation of momentum. So I'm going to write out my thesis to start with. So I'm going to say momentum initial equals momentum final. But we're not really concerned with the linear momentum as much as we are angular. So L for angular momentum. So initial angular momentum equals final angular momentum. Momentum equals mass times velocity. And the rotational analog for that, instead of mass, we're going to use moment of inertia. And instead of velocity, we're going to use angular speed. So I'm going to then write this out again. So we're going to have angular momentum of Mary plus angular momentum of John equals angular momentum of Mary John. Yes. So then we're going to say angular momentum of Mary John, because we're going to do L equals I omega. Angular momentum, Mary John. Oh, actually that's the second part. That's the final when they're together. So we have moment of inertia, Mary, angular momentum Mary, plus moment of inertia John, angular momentum John. Yep. And so now we need to find out what we need to find out. So we want to know the final speed. Yes, the final speed. So this is going to be a question mark. So we're going to start by finding things. So the moment of inertia, Mary. So that is just going to be, I'm going to assume that this is a rotating disk. And so we're just going to look up our moments of inertia. And that's just, it's just a geometric, it's related to the geometry of the shape. So for this, we're going to have a solid disk, which I'm going to assume it is. It could be the same as a solid cylinder. Radius r, mass m, it's going to be 1/2 mr squared. So it's going to be 1/2 mass of Mary, r of Mary squared. And I'm just going to solve that right now because we can. So it'll be 1/2 times 240 times its radius, which is 1.2 squared. And this will just give us a number. On clear, 0.5 times 240 times 1.2 squared. 172.8. 172.8. And that's a moment of inertia, which is kilograms meter squared. So now I'm going to find moment of inertia John. So a moment of inertia John, he's going to be similar to a particle moving. And go back to our chart. Point mass m and a distance r from the axis of rotation. So he's going to be just at the outside of the merry-go-round. So that's just going to be mr squared. Basically, no. The only difference between the two will be 1/2. So John runs around the merry-go-round. We're going to assume it just at the outer edge. Oh, yep, it jumps. Yep, on the outer edge. So this is going to be 1/2 mass John r squared. So it's going to be 1/2 times. I could probably simplify things, but I'm not going to. R is going to be mass of John is 33. 33 times 1.2 squared. Oh, you're right. Not 1/2. Just mr squared. There we go. Good catch. That could have been tragic. 33 times 1.2 squared. 47.52. 47.52 kilograms meter squared. Okay. So now we need to find the angular speed of Mary. Now we could probably do this in revolutions. Actually, I think we are going to do this in revolutions per minute. Yes, we totally can, and we will. So there's a couple ways we could do this. We could convert everything into SI units, which is kind of my comfort zone. That's not hard. The relationship between linear and angular is x equals r theta, v equals r omega, a equals r alpha. And we would use v equals r omega to convert, actually that's what we're going to use for the other part, to convert revolutions per minute to SI units. We do 20 RPMs, so 20, and that's just revolutions per minute. And so we do 1 minute over 60 seconds, and then 1 revolution is 2 pi. So pi is pretty much 3. So 2 times 3 is 6. That becomes 10. And this gives us about 2 radians per second. You should probably actually plug in 3.14 for 5 or so for pi. Calling pi 3 is a little excessive, but that's how we do that. But we're not going to, because I think we can get away with not doing it. So it's spinning at 20 RPMs. 20 RPMs. And that's because I'm going to stick with RPMs because we want the answer in RPMs. So we might not need to convert it. And the angular speed of John, so I wrote up the relationships up here. V equals r omega, which implies that omega equals v over r. So John is going to be moving at 5 meters per second divided by the radius, which is 1.2, I think. 1.2. Yes, 1.2. So 5 divided by 1.2 is 4 and 4.167. And that's going to be radians per second. Now we want to convert that to rotations per minute. So we have 2 pi radians for 1 revolution. Oh, we want to do it per minute, don't we? Times 60 seconds per minute. So we're going to take our previous answer, multiply that by 60 divided by quantity 2 times 3.1415, and make sure we have enough parentheses. Yeah, maybe. And that gives us 39.8 equals 39.8. That seems all right. Revolutions per minute. Okay, so now we have all the data we need here. We're going to go back up to our conservation of linear momentum. So this is initial angular momentum equals final angular momentum. We now have data for all of these. We're going to rearrange this for the angular momentum of Mary and John. And so that's going to be moment of inertia, Mary, times angular momentum of, or angular speed of Mary, plus moment of inertia, John, times angular speed of John. And that's going to be divided by the moment of inertia of Mary and John. So that is just going to be, it's similar to masses. If you have two blocks, the masses are just the total mass of the blocks, just the two blocks added together. Same idea with moments of inertia. Moments of inertia of two items together is just their individual moment of inertia also added. So we got both of those. So writing these out, we're going to have lots of data here. So it's going to be 172.8 up here at the top. That's a point. Times, let's see, this was 20 RPMs. Plus moment of inertia, John, which is 47.52 times 39.8. So John is he's going faster, about twice as fast as the merry-go-round. So we'll expect it to speed up. And then we'll divide by 172.8 plus 47.52. Oh, and I'll put in RPMs here just to be consistent. RPMs. Yep, that seems reasonable. And I'm going to do this on Wolfram just because it's complicated enough. I don't want to put in my calculator. And it's easier to check my work to make sure that, oh, yep, I put it in correctly. Times 20 plus 47.52 times 39.8 divided by 172.8 plus 47.52. Yep, and the merry-go-round actually speeds up. So here's our values, plug it in, 24.27. So the final speed, measured in RPMs, is going to be 24.27 rotations per minute. Yep. Yes, that seems reasonable. Yeah, I'm good with that. So there's 24.27 RPMs. Since John is going faster than the merry-go-round. Actually, I want to check that real quick since I got a second. So if I convert the angular speed of 20 RPMs to radians per second, I already did that, and I get 2 radians per second. So V equals R omega. So the radius is 1.2 times 2. That's about, 2.4 meters per second. Yes. So the merry-go-round is only spinning at the edge right here at about 2.4 meters per second. John is running at 5 meters per second. So it makes sense that the whole system would speed up. All right, so let's backtrack real quick. 24.3 rotations per minute. So this problem here was conservation of angular momentum. So we started with the idea of initial momentum equals final momentum. We then I write it out usually in the linear, just because that's the only formula I memorize. We then convert that, write out the analog, the angular equivalent. Basically we say, instead of using P, we use L. Same concept applies. Initial equals final. And I broke up the initial into 2 parts, Mary and John. I then said that since momentum is mass times velocity, angular momentum is going to be moment of inertia times angular velocity. And so I expanded the angular momentum into moment of inertia and angular speeds. And I got this equation with basically 6 terms. I then went through and found each of the individual terms. One thing we had to do is we had to convert John's linear speed of 5 meters per second to an angular speed, which we did through the relationship v equals r omega, where omega is angular speed. And we looked at moment of inertia, and John, even though he's running in a straight line, he still has an angular momentum with respect to the axis, and that was just mr squared. Found all the individual components, did some algebra to solve for the angular speed of the Mary-John combination, did a bunch of math, and then solved. So this one can be a bit confusing, but once you understand the concepts, I think it's pretty reasonable. So I hope that helped with understanding this problem. See you next time.